So two charges are in the same uniform electric field. Uniform electric field just means it's the same no matter where you are, and that always happens when you have parallel plates. So like this, where one plate is charged positively and the other plate is charged negatively. Then this is just saying that the field in between these two plates is going to be the same no matter where you're standing. Okay, so let's just think about this for a second. Here's the field. Oh boy. No matter where you are, if you are right over here, let's say, you're going to feel, and let's call this a positive charge. Okay, since with fields point in the direction of the force on a positive charge anyway, we may as well make it positive. So this positive charge is going to experience a strong repelling force here, and it's going to also experience a weak attracting force. Okay, so let's just think about this. This positive plate is going to be pushing against this positive charge, right? They repel each other. This negative plate over here is going to be attracting the positive charge. Okay, so this positive charge is experiencing both a repelling and an attracting force. It's just that the repelling force, this one over here, is much stronger right now. Much stronger because that positive charge is much closer to the positive plate. Okay, so right now it's feeling a certain force, and part of it is because of repelling, and part of it is because of attracting. Now let's go over here, right in the middle. We're going to call this a positive charge again. And so now, this positive charge is going to experience less repelling force because it's a bit farther away from that positive plate, but it's going to experience more attracting force than this other one over here because it's closer to the negative plate. Okay, so the repelling force and the attracting force are going to be equal to each other in this case because it's right in the center. And then if you would look down here, now we have the opposite of the first situation happening. If this is a positive charge, now you have a little repelling force from the top plate because it's so far away, and a really strong attracting force because it's really close. Okay, but it's always going to balance out. The force that this charge is going to experience in total is going to be the same as this one, which is going to be the same as this one. Okay, so by uniform, what it means is just that the field, no matter where you're standing in between those plates, is going to be the same. Okay, so two charges are in the same uniform electric field. A 0.2 Coulomb charge feels a force of 1.3 times 10 to the negative 4 newtons north. What is the force a negative 0.7 Coulomb charge feels at the same location? Magically disappeared. So we already know that this force is being experienced to the north, and this charge is positive. Okay, so if this charge is right in here, it's positive, and it's experiencing a north force. Okay, so let's just call this north and this south. Okay, so if it's experiencing a north force, that's got to mean that the positive plate is negative. Does that make sense? Because this positive charge is experiencing a north force, so it needs to be attracted to this top plate. If this was a positive plate at the top, then this positive charge would be repelled from the top plate, and so the electric force would be south instead. So it's got to go this way, which means that the positive plate is the bottom plate. Okay, we don't really need the direction of the field, but we can draw the direction of the field. It's good practice. And so the field points in the direction of the force on a positive charge. We already know the direction of the force on this positive charge. It's north. So it's going to be like this. Rainbow field. Okay, but what we really need to know is that this positive charge is experiencing and northward electric force. It doesn't say anything about gravity, so that's not what this question's about. So, like, we would need to know the mass of this charge in order to do anything with gravity. So this question's not asking us, like the Millikan experiment, how do they keep it in balance or something like that. That's not what this is about. So we're just supposed to solve for what is the force on this negative 0.7 Coulomb charge. What is the electric force there? Okay, we know the force on a 0.2 Coulomb charge, but we don't know the force on a 0.7 Coulomb charge. Okay, now you could probably just use fractions to figure this out, and in fact there's several ways that you could do this. But what I'm going to do first is figure out what's the field that is being experienced by this 0.2 Coulomb charge. Okay, I want to figure out what this field is so that when I take my negative charge and I put it here, then I can figure out what force it's experiencing. Okay, so if I figure out the field, I can figure out the force on this other charge. Okay, and I just want to point out that electric force equals charge times the field strength that it's in. Okay, so we could figure out the force on the 0.7 Coulomb charge because we know it's charge. We just need to know what the field is. And so we can figure out the field using the other two pieces of information. So we're going force equals Q E. Now I'm talking about the first charge now, the 0.2 Coulomb charge. So I want to figure out what the field is. So I'm going to go divide by charge, and that gets me my field is the force divided by the charge. So my field is 1.3 times 10 to the negative 4 newtons divided by 0.2 coulombs. So my electric field is going to be 6.5 times 10 to the negative 4. 6.5 times 10 to the negative 4 newtons per coulomb. Okay, I was dealing with coulombs here. That was my charge. And so my field strength is going to be measured in newtons per coulomb as well. Okay, so this is the field that's being experienced by the positive charge. But if you stick a negative charge in there, it doesn't change what the field is at all. The field doesn't have anything to do with what charge you're putting into the field. It only has to do with what field is being produced by the plates. Okay, so when we take this field and we put the negative 0.7 Coulomb charge in it, we're going to get a different force. It's going to experience a little bit of a different force. And if we think about it, this is a 0.2 Coulomb charge. This is a 0.7 Coulomb charge. Which one should be experiencing a greater force? The bigger charge. The bigger charge is going to experience more force when it's in the same field. Okay, just like a heavier person experiences a greater force of gravity than a light person when they're standing in the same spot. Okay, so now when we actually do that calculation, what's the electric force on a negative 0.7 Coulomb charge? I'm not going to put the negative in. Okay, and here's the reason. This negative is not a direction. It's not a vector. So the polarity of this charge, whether it's positive or negative, is going to have some effect on the direction of the force it experiences, but I'm not going to put it in my formula because it doesn't necessarily tell me the direction that things are happening in. I don't want you to get confused about that. So we're just going to do the calculation without the polarity in it, and then we're going to figure out the direction of the force after that. Okay, so when we put in the 0.7 coulombs, I'm just going to put in 0.7 coulombs without the negative. It's not a vector, it's the polarity. So this is 0.7 coulombs times, I figured out that my field is 6.5 times 10 to the negative 4 newtons per coulomb. And so then when I calculate the electric force on that 0.7 coulomb charge, I get 4.6 times 10 to the negative 4 newtons. Okay, I need my direction now. Okay, but we're just going to think about this. So if we go back to our diagram here, and now we put a negative charge in the middle instead of a positive charge, and I'm drawing with the wrong color. We put a negative charge in the middle instead of a positive charge. Now, notice that it's going to be repelled from that top plate and attracted to the bottom plate, right? A negative charge is going to move toward the positive plate. It's going to move away from the negative plate. So our direction over here is now going to be south, not north. Okay, the force on the positive charge was north, which means that the force on the negative charge should be south. There's our force on the negative charge. And I'd like you to notice as well, notice that this field, the field between the plates here, it's pointing upward, or it's pointing north. Okay, so that's the top plate is north. It's pointing north. That is also the force that a positive charge experiences, because a field is drawn in the direction of the force on a positive charge. When we put a negative charge in there, the force it is going to experience is going to be the opposite of the field. This is the electric force on a negative charge. Okay? Sometimes that's difficult to keep track of, but I think that the more problems you actually do, the better you're going to get at recognizing what's happening.